Welcome you all to the new session. So, in this session we are going to learn the moment of inertia of solid sphere. So, here we are considering a sphere of mass capital M and radius capital R. So, here we are just considering a sphere of mass capital M and radius capital R. Here rho be the mass per unit volume of the sphere. Let rho be the mass per unit volume of the sphere, and rho is given by m by what is the volume of the sphere of radius capital R? It is 4 by 3 pi r cube. So, m by 4 by 3 pi r cube. So, this is the mass per unit volume of the sphere. So, that m is given by mass of the sphere is given by 4 by 3 pi r cube rho. So, this is the mass of the sphere. It is 4 by 3 pi r cube rho. Here x or x dash be the diameter of the sphere, about which we need to find out the moment of inertia. We imagine the sphere is made up of a large number of concentric circular discs. You can see different slices of different radii. The sphere is made up of a large number of concentric discs. Consider one such disc which is at a distance of x. So, consider one such disc which is at a distance of x from the center. Here we are just finding out the moment of inertia of the sphere about x or x dash, which is nothing but it is the axis passing through its center and perpendicular to the plane of the disc. So, we know the moment of inertia of the disc about an axis perpendicular to its plane and passing through its center of mass. For that, first we need to find out the mass of the disc. For that, first we need to find out the radius of the disc for finding the volume of the disc. So, these are the different steps we need to follow. First we need to find out the radius of the disc, then find out the volume of the disc, then find out the mass of the disc. Okay. Here you just imagine this slice, this one, okay, this is that slice. The radius of that disc, it is from this point to this point, right. So, this is the radius of this particular disc. It is not r, r is the what? R is the radius of the sphere. So, this is that one, this r dash is given by y here. So, it is nothing but y, which is the radius of that particular disc. So, here it is y, capital R is the radius of the sphere and x is the distance from the center. So, this is that right angle triangle. From this you can find out the radius of the disc, which is given as y equal to root of r square minus x square, given by y equal to root of r square minus x square. So, I am repeating the steps. First we need to find out the radius of the disc. So, we found out the radius of the disc, which is nothing but root of r square minus x square. Then we need to find out the volume of the disc. So, volume of the disc is given by V equal to volume of the disc is given by what? It is area into thickness. So, disc of radius y, the area is pi, cross sectional area is pi y square into dx, which will give you the volume of the disc. So, it is pi y square dx, and we know what is y square? It is pi into r square minus x square dx, pi into r square minus x square dx. Therefore, the mass of the disc equal to what? Volume into mass per unit volume. So, it is pi into r square minus x square dx into rho, which will give you the mass of the disk. So, we arrived at the expression for the mass of the disk. Next, we need to find out the moment of inertia of this disk about x or x dash, which is nothing but the axis which is passing through its center and perpendicular to its plane. It is given by half into mass into radius square. It is m r square by 2. So, moment of inertia of the disk about x or x dash equal to mass of the disk. It is pi into r square minus x square rho dx, mass into radius square. What is radius? Root of r square minus x square. So, the square is r square minus x square. So, it is y square divided by 2. This will give you the moment of inertia of the disk about x or x dash. So, it is pi by 2 rho into, it is equal to pi by 2 rho into r square minus x square the whole square dx, r square minus x square the whole square dx, which will give you the moment of inertia of the disk about x or x dash. So, we can imagine the sphere is made up of a large number of such disks. So, the moment of inertia of the whole sphere is nothing but the moment of inertia of all such disks about the axis x or x dash. So, you need to integrate this expression from minus r to plus r. You need to integrate the expression from minus r to plus r, or twice into integral 0 to r. So, it is given by I equal to which is nothing but the moment of inertia of the sphere about x or x dash, I equal to 2 into integral 0 to r, 2 into integral 0 to r, pi by 2 rho r square minus x square dx, pi by 2 into rho into r square minus x square the whole square, r square minus x square the whole square dx. Here whole square is there, r square minus x square the whole square dx. So, here pi rho 2 cancel, pi rho is constant, take outside. So, pi rho into integral 0 to r square minus x square the whole square dx equal to pi rho integral 0 to r a minus b the whole square, a square minus 2ab plus b square. So, it is r raised to 4 minus 2r square x square plus x raised to 4 dx. So, integrate time by time, it is r raised to 4x minus 2r square x cube by 3 plus x raised to 5 by 5 and apply the limit 0 to r. So, that you will get pi rho into, you please integrate the expression and then apply the limit. So, it is r raised to 4 into x, right. R raised to 4 into x means r raised to 4 into r, which is nothing but r raised to 5 minus 2 into r square x cube by 3, 2 into r square x cube by 3. So, just apply the limit r. So, r square into r cube by 3, which is nothing but 2 into r raised to 5. So, r square into x cube by 3, apply the limits r cube by 3 to, so 2 r raised to 5 by 3 plus x raised to 5 by 5, apply the limits r raised to 5 by 5, r raised to 5 by 5. Take the LCM as 15, then solve, so that you will get what, 15 r raised to 5 minus 10 r raised to 5 plus 3 r raised to 5, which is nothing but, it is given by pi rho into 8 r raised to 5, 8 r raised to 5 by 15, 8 r raised to 5 by 15. So, here what is the expression for the mass? The mass is 4 by 3 pi r cube rho, right, 4 by 3 pi r cube rho. So, we need to group these terms 4 by 3 pi r cube rho here. So, equal to 4 by 3 pi r cube rho. So, 4 by 3 pi r cube rho. So, what is remaining? 4 by 3 pi r cube rho into 2 is there because 8 is here. So, we take 4, then 4 into 2 8. So, 2 is there, 2 into r cube is here, total r raised to 5. So, r square by here 15, here it is 3. So, 5, 4 by 3 pi r cube rho into 2 r square by 5. So, that you will get it is 8 by 15 and the same is given by this is m 4 by 3 pi r cube rho, it is m. So, the final expression for the moment of inertia equal to 2 by 5 m r square. So, the moment of inertia of the sphere about its diameter is 2 by 5 m r square. So, this is a very important derivation. We need to expect the same in our exam also. This is the moment of inertia of the sphere about the diameter. Here we will consider the sphere is made up of a large number of concentric discs, and we are just imagine one such disc which is at a distance of x, and that y be the radius of that disc. So, the first step is you have to find out that radius y. Then you please find out the volume, then the mass of the disc. After finding that mass of the disc, find the mass of the disc about the axis x or x dash, which is m r square by 2. So, you will get this expression. From this expression you can get the final expression by integrating the same. So, the moment of inertia of the sphere about the diameter is 2 by 5 m r square. Next is moment of inertia of the same sphere about the tangent. So, it is very easy for you, I think, I hope so, because we know the moment of inertia of the sphere about x or x dash. Now, we need to find out the moment of inertia about AB, which is the tangent. How? What is the method? Just use parallax theorem. Just use parallax theorem. The moment of inertia of the sphere about the tangent I equal to moment of inertia of the sphere about x or x dash, which is ICM plus ICM plus the mass of the sphere, it is m, mass of the sphere, it is m, into the distance between the axis, it is nothing but the radius m r square. So, what is ICM? What is the moment of inertia about x or x dash? It is 2 by 5 m r square, 2 by 5 m r square plus m r square. So, 2 by 5 m r square plus m r square, which is nothing but 7 by 5 m r square, 7 by 5 m r square. So, this is the moment of inertia of the sphere about its tangent. So, two things, moment of inertia of the sphere about the diameter and the moment of inertia of the sphere about the what? About the tangent. So, we have learned the moment of inertia of so many shapes. We learned ring, disc, cylinder, sphere. In all these steps we have followed only 3 steps. What? So, just remember, we have followed just 3 steps. First we identified a small element, then we found out the moment of inertia of that small element about the same axis, then we integrated the expression. In all the derivations we use the similar steps. So, this is the final shape, which is the sphere. So, the moment of inertia of the sphere is given by 7 by 5 m r square. So, next we need to learn the kinetic energy of rotating bodies. We know when a body is moving along a straight line or when they execute translatory motion with a velocity v, we have the kinetic energy which is given by, if m is the mass of the particle moves with a velocity v, the kinetic energy expression is half mv square in the case of translatory motion. But here we are considering rotational motion. So, instead of v, we need to find out the angular velocity. So, here we are imagining a body of mass capital M, and the body is made up of a large number of particles, and we are just identifying one such particle m1 which is at a distance of r1. So, when the body is rotating about a fixed axis, all the particles will rotate with same angular velocity omega, but different velocity, but different linear velocity v. Okay. So, that is the case. Here the particles will execute the rotation motion with the same angular velocity omega, but their linear velocity will be different. So, you have to identify what is the difference between this linear velocity and angular velocity. Here suppose this is a circular path, the particle is executing a circular path like this. So, this is the mass. Okay. So, at any instant the linear velocity of this particle will be along the tangent. So, this is v. Linear velocity of this particle is along the tangent v. So, what is this angular velocity? Angular velocity is given by omega equal to what? Angular displacement by time taken, theta by t. So, this is the expression for angular velocity. Linear velocity, displacement by time taken, angular velocity, angular displacement by time taken. For example, at the initial state the particle is at this position, then it makes an angle theta and reaches to this point at a time t, then we can say omega equal to theta by t. So, what will be the direction of this angular velocity? Do not confuse it with it is along the tangent. Okay. The direction of the linear velocity is along the tangent, but for finding out the direction of the angular velocity, just curl your finger in the direction of that rotation. If it is anti-clockwise, just curl your finger in this manner, and the thumb will give you the direction of the angular velocity. Okay. It is along the axis of rotation, and the direction of the thumb will give you the axis of rotation. So, if it is in the anti-clockwise direction, if the object is revolving in the anti-clockwise direction, the angular velocity will be along this direction. Okay. So, this is the direction of angular velocity and linear velocity. Okay. So, suppose in this case the particle is executing the rotational motion with angular velocity omega. Let v1, v2, v3 be the velocities of the linear velocity of the particle of mass m1, m2, m3 etc., which are at distance of r1, r2, r3 etc. So, kinetic energy of the particle of mass m1, kinetic energy of the particle of mass m1 is given by m1 is given by, you know, it is half m1 v1 square, and kinetic energy of the particle of mass m2 half m2 v2 square. Or instead of, what is the relation between linear velocity and angular velocity? V equal to r omega. So, this is the relation between linear velocity and angular velocity. So, it is given by half m1 half m1, instead of v1 just substitute r1 omega. So, it is r1 square omega square. So, kinetic energy of the mass m1 is given by half m1 r1 square omega square. Similarly, for the case of m2, half m2 r2 square omega square. So, if you want to find out the total kinetic energy of the body, just sum all the kinetic energies of the particles. So, which is given by kinetic energy of the body is given by, it is half m1, it is half m1 r1 square omega square plus half m2 r2 square omega square plus etc. Plus half m3 r3 square omega square plus etc. Just take omega outside because all the particles are executing the circular motion with same angular velocity. So, half omega square into m1 r1 square plus m2 r2 square plus m3 r3 square plus etc. Okay, half omega into m1 r1 square plus m2 r2 square plus m3 r3 square plus etc., or it is given by half omega square into sigma m r square. I is equal to 1 to n m r square. And what is this one? We discussed this one in the first slide. It is nothing but the moment of inertia of the body. So, it is nothing but the kinetic energy of a rotating body is half I omega square. So, the equation is very important. So, kinetic energy of the rotating body is given by half I omega square. Suppose the body is rolling on the horizontal plane. So, this is a horizontal plane and the body is rolling, so that it has both kinetic energy of it has both translatory motion and rotation motion. So, it is a rolling motion. So, in that case the kinetic energy is given by the sum of translatory kinetic energy, which is half mv square plus rotational kinetic energy half I omega square. So, in the case of the rolling body, you have to find out the sum of translatory kinetic energy, which is half mv square plus half I omega square. We need to use this formula for in the while we discuss the problems. So, this is the case of the kinetic energy of the rolling body, and this is the case of kinetic energy of a rotating body. So, this is very important, and we have learned the moment of inertia of different shapes, then we learned the kinetic energy of rotating as well as rolling bodies. So, with this I would like to conclude this session. The next session we will see a very important topic, which is flywheel, and we will see how to find out the moment of inertia of the flywheel. So, bye for now. Thank you.